Back at AP Review, this is 2018 AB Free Response 4. Yeah. So we're given a table, T in years and H of T in meters. Before you even read the problem, you're going to be asked to do two things when you're handed a table like this. Sorry, it got all messed up. All right, you're gonna have to do two things. You're gonna have to find the slope of this thing to estimate the derivative of whatever this quantity is. It's going to happen. You're going to be asked to use old school slope to try and estimate this thing's derivative. You're also going to be asked to estimate the integral of this thing using one of the area approximation methods you know, like trapezoidal or MREM or RREM or LREM. It's going to happen. So if you know that going into a table problem, if you say, hey, this is what's going to happen, it can kind of ease some of the stress going into it. So the actual write-up for this problem says the height of a tree at time t is given by the twice differentiable function, just meaning we can derive the function twice, h, where h of t is measured in meters and t is measured in years. Selected values for h of t are in the table. Use the data in the table to estimate h prime of 6. Using the correct units, interpret the meaning of h prime of 6 in the context of this problem. So that's the first thing I said that you're going to have to do, right? So we don't have the time at 6. Right? We don't have the time and height at 6, but we do have 2 points really close to 6. We have t is 5 and t is 7, so we're going to use h of 7 minus h of 5 over 7 minus 5, which is just old school slope, y2 minus y1 over x2 minus x1. And we're going to get that this is a 5, right, 11 minus 6, over a 2. And because h was measured in meters and t was measured in years, we're going to get meters per year. So that's my h prime of 6 approximation. And then when I'm asked what that represents the rate of change of the height of the tree at 6 years. So what this represents is the rate at which the tree is changing height when time is 6 years, right? So after 6 years, so it is growing because this is a positive number, right? It's growing 5/2 meters per year at that moment, right? Part B, explain why there must be at least one time from t is 2 to t is 10, the open interval, such that h prime of t is 2. Okay, so whenever you hear a must in a problem like this, it's using one of the theorems. It's using intermediate value theorem, right, which says that if you have a value above some quantity and a value below some quantity and your function is continuous, you have to hit every y value between. Or it's the mean value theorem, which says that the average slope, old school slope like this, has to equal the instant slope, which would be the derivative, at some point on the interval. And again, all of these things are for differentiable continuous functions. So for part B, since they're asking us about h prime, they want us to show that h prime of t has to be 2 for some value. That's probably going to be the mean value theorem, right? So remember that the mean value theorem says that h of t has to be continuous and differentiable on the closed window. Now it's a closed window from A to B, right? Well, the problem is they gave us an open window from 2 to 10. They didn't include 2 and 10, which means they want us to use some other points in the window from 2 to 10 that we can include. We know that h of t is continuous and differentiable because they said that h of t was twice differentiable, right? Twice differentiable. And you can't be differentiable without being continuous. So in order to be differentiable, you have to be continuous. So I can definitely use the mean value theorem. So now what I need to do is I need to pick 2 points on the interior of this thing that give me a slope of 2, right? So based on the mean value theorem, if I pick any two, so I pick some points on the interior. I can't pick 2 and 10 because they're supposed to be included in the mean value theorem, and they did not include 2 and 10. So I could look at, like, we already know the slope from 5 to 7, so it's not those 2 points. And if I look at the slope from 3 to 7, I don't end up with a slope of 2, right? I get 11 over 2, or 11 minus 2, which is 9, over 4. 9/4 doesn't work. But if I look at these 2 points, they'll give me a slope of 2. So by the mean value theorem, so instead of saying just random A and B, I'm going to say that I know that h of t has to be continuous and differentiable on the window from 3 to 5. So by the mean value theorem, right, by the mean value theorem, h prime of some c in this window has to equal h of 5 minus h of 3 over 5 minus 3, right, which is definitely a 4 over 2, which is a slope of 2. So for some c in the window, the open window from 3 to 5. Well, since 3 to 5 is in the open window, right, so this is in the window from 2 to 10, right? So by the mean value theorem, I have to have some value c in that window where, so h of t equals 2 in the window to 10 for some t, right? So essentially, whenever you hear must, they're asking you to use one of those theorems. The two big theorems that you need to know, technically it's 3. The two big, well, that's not fair to say that it's only 3. The big ones you need to know are the first fundamental theorem of calculus, the second fundamental theorem of calculus, the mean value theorem for derivatives, which is this guy, the mean value theorem for integrals, which is just how you find the average value of a function, and the intermediate value theorem. If you know those, you are probably mostly fine on any calculus test. Those are the big ones. So, cool. Part C is the other thing I warned you would happen at the start of this problem. Use a trapezoidal sum with 4 subintervals indicated by the data on the table to approximate the average height of the tree over the window from 2 to 10 inclusive. So here's a funny thing. This is actually using both the thing I warned you would happen at the beginning and also that mean value theorem for integrals, because that's how you find the average value of a function. So part C, we need to know that the average height, right, average h of t on the window from 2 to 10 is 1 over 10 minus 2, the integral from 2 to 10 of h of t dt, right? This is the actual average value, right? So if I want to clean that up a little bit, I get 1/8 the integral from 2 to 10 of h of t dt. So this is the actual value. But then I want to approximate that, right? I want to take this value, this 1/8 the integral from 2 to 10 of h of t dt, and I want to approximate it using a trapezoidal sum. So I get a 1/8 in front because that's from this. That has nothing to do with the trapezoidal sum. So now when I go to do my trapezoidal sum, so my heights are the distances between these guys, right? And those are my 4 distances, right? And then these are my bases, like base 1 and base 2, and then base 1 and base 2, and then base 1 and base 2. Because these trapezoids aren't of equal height, you can't use a shortcut. So the first trapezoid, the one that goes from 2 to 3, is going to have, so 1/2, the height from 2 to 3 is a 1, and then the sum of these two bases is a 3.5, right? That's my first trapezoid. Plus, my next trapezoid goes from 3 to 5, so 1/2 my height, which is a 2, because it goes from 3 to 5, and then the sum of the bases is a 6 plus a 2, which is an 8, right? Plus, my next trapezoid should be a 1/2. The height from 5 to 7 is a 2, right? Times the sum of the bases, which is a 17, right? 6 plus 11. And I'm barely going to make it on room. 1/2, the last trapezoid has a height of 3 because I go from 7 to 10. And the sum of the bases is a 26 because it's 11 plus 15. And I barely made it, but it's okay. We're going to clean it up. Now, the AP needs to see this. When you look at scoring guidelines for this kind of thing, you'll notice that the AP gives you 1 point for this approximation, or for the trapezoidal formula, rather, and 1 point for the actual approximation you're supposed to get at the end. The reason is they know that there's a good chance you're going to do something silly and accidentally get the wrong number. So do yourself a solid and be like, cool, I'm not going to be too miserable about this. So what I'm going to do, and you don't have to, but I'm going to go ahead and yank out all these 1/2s, because you see how they all have a GCF of 1/2? I'm just going to make my life a smidge easier by yanking out the 1/2 and making this a 1/16, right? 1/2 times the 1/8. And then I can clean things up a little bit. This is a 3.5, right? Plus a 16, plus a 34, plus a 16 and 18, so a 78. Seems about right. Okay, and then I'm going to clean this up a little bit more. So if it were me, it's up to you. I mean, you can definitely leave this as something fairly ugly. I'm going to suggest that there's a couple different options I could take here. I might just go ahead and make everybody, I'm going to probably put these guys together and then make everybody halves, right? These guys together are a 50, which means that these guys together are a 1/28, right? So I get a 1/16. This is a 7/2 plus a 256 over 2, I believe. It's hard to know. So I end up with a 263 over 32, and then we look at the AP Solutions Guideline, woohoo, and we are right. So the AP is not crazy. They know that there's a chance that that's going to fall apart. And then because this is a problem with units, I should make sure that I put units. This is meters, right, because it's the average height. So 263 over 32 meters. They give you 1 point for getting to this final answer. If you're on an AP and you're out of time and your brain is just bailing, make sure you get the setup right? And worst case scenario, make sure you include the word meters, even if you didn't finish it out, and then lose your point for not finishing it out. It happens. Part D. Oh, that's a lot of words. All right. Part D, the height of the tree in meters can also be modeled. Okay, so now we have a totally different problem. That's what they're doing here. They're turning it into a different problem. The height of the tree in meters can be modeled by the function g, where g of x equals a 100x divided by the quantity 1 plus x, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. According to this model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? So here's what they did. They basically changed it up on you and gave you a totally different problem. Still talking about a tree, it's the same tree technically, but aside from the fact that the units are still related, nothing else is even remotely involved. So they do this a lot when there's only certain predictable problems they can give you. Like that table I told you about at the beginning, there are predictable ways that they can take that direction. Like there are directions they can take that problem, and when they run out of directions, they just give you a different problem. So we have that g of x is 100x over 1 plus x, right? We are told that when the tree is 50 meters tall, right, so g is 50, the diameter is, so when g equals 50, right? Dx dt, right? The rate of change of the diameter is 0.03 meters per year, right? They ask, and so that's what we know, right? And they ask, according to this model, what is the rate of change of the height of the tree? So what is dg dt, right? When g is 50. That's what they're asking, right? This is a related rates problem. So you have g equals 100x over 1 plus x. This is your equation. You don't even have to do the diagram and the rates for the related rates. You're just going straight to the equation. When you derive, so we'll put it here. We'll go, because this is dreads, right? You don't even need the D and the R, right? It's actually dread saw for answer the blasted question at the end of the whole thing. Then I derive, but I have to derive with respect to t. So the derivative of g with respect to t is just dg dt, which is totally the thing I want, so that's convenient, right? And that's going to equal, and then I derive this guy, right? So low, 1 plus x, d high is a 100 dx dt, which we're going to deal with in a sec, right? Minus high, which is the 100x, d low, which is just a dx dt, right? Draw the line, square the low. Okay, so that looks kind of disgusting. Super duper fun times, right? But what we need to do now is then we need to substitute in specific stuff, right? We want dg dt at the moment when g is 50. So in order to find out what in order to find that quantity, we really need to know what x is when g is 50. So I'm going to take this original function, right? I'm going to come over here and say, okay, cool. If I know that 50 equals 100x over 1 plus x, when I multiply the 1 plus x over, I get 50 plus 50x equals 100x. 50 equals 50x. Oh, x is 1. Cool, that's great. So now I know that I'm also plugging in x is 1. So I say dg dt at the moment when x is 1 and g is 50 and dx dt is 0.03, right? That's what I'm plugging in. I should be able to find this number. So if x is 1, I'm going to get 1 plus 1 times 100 times a 0.03, which is actually much nicer than you'd expect because yay 100 to get rid of that decimal, minus a 100 times a 1 times a 0.03, also again thanks to the 100, over a 1 plus 1 quantity squared. So I get that this is a 2 times a 3 minus a 3 all over a 4. So I end up getting 3/4, right? And again, g is measured in meters the same way as the other one, so this would be meters per year, right? So dg dt would be meters per year. And they asked me, according to the model, what rate is that? Yep, and that's what they want. So there you go.